Section 2.2b, we're going to look at density curves and assessing normality. All right, so first question is, what is a density curve? All right, it's a curve that we can use to model a distribution, okay? And so like the last lesson we looked at the normal curve and the normal distribution, that is a type of density curve, all right? But it's not the only type, so we can look at some other ones. So here's an example of a density curve. This dot plot shows the amount of time it takes Selena to get to the bookstore by train. And the way we could model that with this density curve is this straight line. Now, a density curve is an approximation, just like we saw last time when we were talking about the normal curve, where it's not exactly, real world data is not exactly normal, but we can use the normal distribution as a good estimation. Same thing here with these other density curves. So obviously if I look at these dots, the top of the dots does not form a straight line straight across. But somebody with a lot more time in their hands did a lot of math and found out that the probabilities that we get from this is close enough to what actually happens in that dot plot. Okay, so some things to know about this density curve. First thing is, why is this height here 1/3? And the answer is the probability is the area under the curve, just like it was with the normal curve. And so that has to equal 1, because the probability of all of the possibilities together has to equal 1. So if I look at the journey times that she has, they are all between 2 and 5 minutes, all right? So that's a 3-minute span. So if I want the area of this rectangle to equal 1, if the width is 3 and the area of a rectangle is width times height, all right, or length times height, however you want to write it, okay, if this is 3 and I need the answer to be 1, then the height has to be 1/3. So we always assign the density curve a height so that the area underneath the curve is equal to 1. And then very similar to our normal curve, we can use this to find probability. So what percent of the time does Selena's trip take more than 4 seconds? All right, so that would be from here to here, this blue shaded area. And because the curve is a rectangle, unlike the normal curve, I don't need a big table or a fancy calculator. I can literally just find the area of this blue rectangle. It has a length of 1 second and a height of 1/3. So 1 times 1/3 would be 1/3, or 33.3% of the time. Okay, this would be another example of a density curve. This would be like a normal curve, so we could roughly approximate this histogram as that kind of curve. We can also have curves that are skewed, like this one, okay? Things you need to be able to find would be the mean and median of a density curve, okay? The mean is like the balance point. So if we think about where would the balance of the curve be, like if it was made out of solid material and I was going to try and balance it on like a seesaw or something, okay? And then the median is where the area under the curve is divided in half. Okay, and just like we talked about before, if I have a symmetric curve, then my median and my mean are going to be roughly the same. If I have a curve that is skewed to the right would make the mean greater than the median, and then skewed to the left would do the opposite. So something that's important in statistics is to be able to assess normality or decide whether or not a distribution is approximately normal, because that tells us whether or not I can use z-scores, whether or not I can use my calculator, my normal distribution menu. All of those things are very important. So here we have Chapter 1 test scores for Mr. Finn's AP Calc class, and we want to know, is the distribution approximately normal? All right, different ways we can tell. One is we can look at a graph. Okay, so if I looked at a histogram or a dot plot of Mr. Finn's calc scores, all right, we would be looking for 3 things. Okay, is the graph roughly symmetric? Does it have a single peak in the middle? and then is it bell-shaped, all right? If it does not meet all three of these qualities, then we would say it is not approximately normal. So if we had a graph of Mr. Finn's test scores, this is what it would look like. Here's a histogram. Okay, roughly symmetric shape, yes. Single peaked, all right. One like general area between 75 and 85 is the highest, and then bell shaped, meaning the peak is in the middle and the two sides are symmetric. So I would say yes, Mr. Finn's test scores are approximately normal. Another thing we could look at is what we briefly talked about last time with the 68, 95, 99.7% rule. Okay, so remember, those should be the percent of the data points that are within 1, 2, and 3 standard deviations of the mean. So we can actually count our data and see if it roughly matches those percentages. All right, so here's some more information for you, some summary statistics, all right, and then the list of the test scores again. So what we want to know is how many test scores are within 1 standard deviation of the mean. Okay, so the mean is 81.031. If I add and subtract the standard deviation, I'm looking at the range from 74.523 to 87.539. If I count the number of data values that fall in this range, that would be 21. 21 out of 32 is 65.6. Okay, we're going to do the same thing for 2 and 3 standard deviations. So for 2 standard deviations, I'm going to add and subtract 2 times 6.508. So that gives me this range of 68.015 to 94.047. And again, if I count, that's 30 out of 32 values, which is 93.8%. And then for 3 standard deviations, all of my values, 32 out of 32, so 100% are within 3 standard deviations. Okay, so we got 65.6, 93.8, and 100. Okay, it does not match exactly 68, 95, and 99.7, but it's very close. Okay, again, it's never going to be perfectly normal. But as long as we are close, we would say that the Chapter 1 test scores are approximately normal based on both the graph and the 68, 95, 99.7 rule. Okay, something that is important for you to note here. We would never say that a distribution is normal. Okay, we never say anything is perfectly normal. We are always going to use the word approximately. Okay, so we would say that this distribution is approximately normal because it roughly follows the 68, 95, 99.7 rule. Okay. 2 other ways that we can use to assess normality, a little bit less common, but if we look at those summary statistics, the min and the max should be approximately the same distance from the mean. Again, that would tell us whether or not our curve is symmetric. You can also look at the distance of Q1 and Q3 from the median. Those should be approximately the same. Again, they're almost never going to be exactly the same because that's not how real life works. But we're looking for them to be within, a few units of each other. Again, dependent on your units. So, if we're talking about test scores, maybe they should be within 4 to 6 points. Talking about population of a country, now we're talking about hundreds of millions of people, so that distance can be a little further, so it should always be in context of your units. The other thing we can look at is something called a normal probability plot. It's a scatter plot that can be made in your calculator, and it has the data value and its expected z-score. So if we use the percentile and we assume that the distribution is normal, we would look at what that z-score would be and then compare it to the actual data point. And what we're looking for is for it to be a straight line. Okay, again, not going to be perfect, but if it's roughly linear, then that's another indication that our data is approximately normal. So here are 2 examples. Okay, again, we got a little squiggle here, we got a little squiggle going on there, but each of those, if we roughly tried to draw like a line of best fit, it would be roughly linear. Okay, so both of those, if that was what our normal probability plot looked like, I would say that distribution is approximately normal. So to give you an idea of what it looks like when there's not, okay, it'd be something like this. So this part of the graph might be linear, but then there's this big long tail over here that flattens out. All right, so that distribution is not approximately normal. That distribution looks like it would be skewed to the right with these two outlier dots out here. All right, and that's all we have for 2.2b.